All right, so just to go over some of these questions, if you had any um, questions on them. For number two, I think number one was straightforward. For number two, we can just go through them. So it says, how far does the toy car travel in the first 2 seconds? Well, here's 0, 1, 2 seconds. Well, how far are you at 2 seconds? It went 2 meters. Okay. Then it says, what is its average velocity during the first 2 seconds? Well, where's the starting point? 0, 0 is your x1 and y1 coordinate, and 2, 2 is your y2 and x2 coordinate. So just do our normal average, y2 minus y1 over x2 minus x1, and you're just getting 2 over 2, so I get 1. And our units is, what are we, meters per second. When does the car move to the right and to the left? This one is saying we're still assuming it's that goofy picture from class. So it starts off, just quite literally going to the right. It moves 2 meters to the right. And when does it stop moving to the right? Well, look at the graph. It moves 2 meters away from the starting point. So that's when it's moving from the right, from in between 0 to 2. So any time in between 0 to 2, it's moving from the right. And to the left, the whole rest of the time, well, it's got to go back 2 meters. And then look, it continues in that direction. So it continues after time 2. It's just continually moving to the left. And you could say it either stops, here, or it just continually moves to the left. When does the car return to the starting point? Well, again, look at the graph. It returns to the starting point. It goes 2 meters and back. This is that starting point, right? It goes 2 that way, and then it comes back. We're just talking about some random linear track. So that's at time 4, right? T equals 4. What is the instantaneous velocity at time 1, 2, 3? Well, we don't have a function to take the derivative of, but we have our graph, so we're just going to estimate. At time 1, approximately, what's our instantaneous velocity? Well, I don't know. What's that slope look like? It looks about 1 meters per second, right? At time 2, well, at time 2, that one, there's no question. That one is going to be 0, right? And then the instantaneous velocity at 3, well, I'd make the argument if you call this one positive 1, we'll call that negative 1. And again, this is just an estimate, meters per second, that is. If you want to say that's negative 2, fine, go for it. And that's 1 over there, that's fine, or 2. And again, meters per second. At what time does the car move fastest to the right? And again, we want to really think about what fastest means when we're looking at a graph or thinking about velocity. We're talking about when is our slope the steepest, right? So fastest to the right, we're talking about the highest slope, positive slope. So that over here, that looks like it's at 0, right, when it starts. So I would say it was, at time 0. Fastest to the left, well, where's the steepest slope? If you kept drawing these tangent lines here and here, it's probably right about here, right? That actually looks like our inflection point, and that's where we know the slope is the steepest, right? So I would argue also at time 4, it's moving the fastest to the left, right, at t equals 4. And then what is the farthest the car moves to the right during the first 6 seconds? Well, the furthest it goes to the right is just that 2 that we already talked about. 2 meters. All right, number 3. Here we can actually start to do a little graphing, or a little, actually, we have our equation, so we can do some of our calculus there. So it says a particle moves along a line so that its distance in meters to the right of its starting point, t seconds, after t seconds, is this equation. All right, so does the particle begin moving left or right from the origin? Well, they're telling us this, meters to the right of its starting point, is when I have a positive number for s of t, that's our position, we're saying that's meters to the right. When I have a negative, that's what it's saying is meters to the left. So that's why they're telling us this part, so that we know when we have positive numbers that come out of our function, it's to the right, and negative is going to be to the left. So what does it begin moving? Let's put in a 0, and what does our value equal? What if I put in a 0, I get 0 minus 0. Well, that's not helpful. I just get 0, right? We'll put in something really small after 0. Well, if I put in a 1, I get 1 minus 5. I get negative 4. Right, it's starting off in that negative direction. You could also look at the velocity, right? If we find our velocity equation, s prime of t equals, we'll fit it down here, 2t minus 5. So our first derivative is our velocity, right? What happens at time 0? Well, if I put in 0, well, I get a negative, right? My slope is negative. So again, if we look back in like the graph when we were talking about meters to the right and to the left, well, anytime my slope was negative, right, I was moving to the left. So that's another reason why it's moving to the left. Where does it begin? Where is the particle after 1 second? Again, where? We're talking about our position function, right? Don't do anything with velocity. It's just where is it? We'll put in a 1. If you put in a 1, 1 minus 5, like we said, is going to be negative 4. And what do we mean by negative 4? Well, again, we said that negative meant to the left of where it started. C, how far does the particle move in the first 2 seconds? All right. Just, again, how far, we're talking about where is it? Plug in a 2. Well, if you plug in a 2, you get 4 minus 10, you get negative 6, right? It moved 6 meters to the left. D, what is the average velocity over the first 2 seconds? And again, for average velocity, we're not really using our velocity equation. We're going back to x2 and y2 and x1 and y1, right? If we come down here and say, okay, well, if our average velocity, we're just talking about slope. So we have x2 is 2 after 2 seconds. x1 is 0. That's the starting place. Plug in a 0 to get your y1. Well, that's just 0. Plug in a 2 to get your y2. And we already said that was negative 6. So we get negative 3, right? Negative 3 meters per second is going to be our average velocity over the first 2 seconds. When does the particle return to the origin? Again, this when question, we're talking about our position, right? When does it return to the origin? And again, we'll come down and do our work here. When is it back at 0, right? When is it back at that starting point? Well, just solve the initial equation. We're talking about really our x-intercept. So we can solve this just by factoring. We get t minus 5. So I have 2 answers, right? I have at time 0, but that's where we started, so that's not going to be our answer. So it's the other one, the other solution, at time t equals 5. We're back to the origin at 5. What is the acceleration of the particle at time 1 and 2? Well, velocity is our first derivative. To find our acceleration, that's our second derivative. So if we take our second derivative, we just get what number? We just get 2. So that's a constant acceleration. Doesn't matter if it's at time 1 or time 2. There's no t's to substitute in. The acceleration always 2. And again, our units are meters per second squared. Question 4. Suppose a particle moves along a number line and its position to the right of its origin is given by that function where t represents time. All right, so A, if s of t, right, the original function, that position is less than 0, then the particle is doing what? What is it doing? Where is it? How can we describe it? If we're talking about the original function, if it's less than 0, if that y value is less than 0, we said that was at the left, to the left of the origin, right? Again, if we look at this question or a question with a graph, if the original function is less than 0 anywhere in this portion over here, that means it's to the left of the starting spot. If s prime of t, right, the slope, the velocity, if it's greater than 0, then what's the particle doing? Well, if the slope is greater than 0, then the particle is moving to the right at that time, right? If your slope is positive, well, you're moving to the right. And again, we could look at that graph, even though we didn't have a function. Anytime our slope was positive, right, we were moving to the right. As soon as our slope was negative, like we said, that whole part, we were moving to the left. And lastly, s double prime, right, that's our acceleration. If s double prime is less than 0, so we're decelerating, then the particle is, well, I would just exactly say what we just said. It's decelerating. I'm not going to print that with my sloppy mouse writing, but the particle is decelerating at that time. That's what it's telling us. All right, in our last question, it says a ball is thrown upward from the top of an 80-foot building. So that's our initial position, right? So that its height in feet above the ground after t seconds. Again, this is our position function. There's our initial position. This is that initial velocity, and this is our constant for eventually we'll get our acceleration out of there, right, if we take our second derivative. So there's our equation. It says find the average velocity. Well, hopefully by this point, we just know our average velocity is plug in x1, plug in x2 into our original function, and that's just our slope, right? Divide. If you sit there and divide, you'll get what the book has. I believe it's 32 feet per second. All right, instantaneous velocity. That's saying, hey, it's derivative time. Well, what's your instantaneous velocity at time t? Come to your original equation, right, and take your derivative. So h prime of t is, well, the 80 goes away. We just have 64 minus 32t. That's our velocity, our instantaneous velocity at any time. If we want to know what's the instantaneous velocity at 1, we'll plug in a 1. If I plug a 1 in for t, I get 64 minus 32, so I'm going to get 32 feet per second. All right, C, when is the velocity equal to 0? When is the velocity equal to 0, right? What are we going to do now? Well, set the velocity equal to 0 and solve. Well, if you set your velocity equal to 0 and solve, you can bring over your 32, right? Add 32 to both sides, divide by 32, and you get time 2, right? So at time 2, your velocity is equal to 0. Well, what is that? When we're doing our graphing without any applications, that's our max or min. We kind of know from looking at our equation, this is some sort of upside down parabola, and that's where our max or min is. So at time 2, on our x-axis, or t-axis, we're at our max. Well, that's our next question. What is the ball's maximum height? Okay, well, take your 2 and plug it into your equation, right? Your original equation. That gives you your position. So if you plug in a 2 for t, 80 plus 60 times 2 minus 16 times 2 squared, we're going to get 144, just like the book says, 144 feet. E, when does the ball hit the ground? Well, where's that spot? When, right? We're just back to when does it hit the ground? When is our position 0, right? We're just taking that and setting that equal to 0. 0 equals that 80 minus 64t minus 16t. I'll do this on the board because this is going to get sloppy. 16t squared. Okay, I bet you could factor something out and do it without a calculator. Try. Right, so initially I put a minus here by accident. That should be plus, it says. So what are we looking at? Well, I noticed you could take a 16 out of everything. So if you divide 16 out of everything and rewrite it, because you want to have t squared first so that we could factor a little more easily. Well, what multiplies to negative 5 and adds to negative 4? Well, that's negative 5 and 1. And so my two t's are going to be at negative 1, which makes no sense in an actual application when we're talking about the time it hit the ground. So at 5, at time 5, that's when we're hitting the ground. For what values of t is the ball falling? Well, after our max, the ball is always falling, right? So in between 2 and 5, or 2 and negative infinity, but again, our ball isn't some crazy thing that goes through the ground and goes through the earth, so in between 2 and 5. What's the acceleration at time t? Well, acceleration, we have our first derivative. Take your second derivative. So h double prime of t equals negative 32, right? And it should be, if this is a particularly real-world equation, it needs to be negative 32 because that's in feet per second. That's our gravitational, feet per second squared, that is. That's our gravitational constant or acceleration for the Earth, right? The negative saying that downward pull. And lastly, graph the function h of t. Well, you don't really have to do that. We kind of have a rough sketch right here, right? We know this is negative 1 where it crosses. That's 2, comma. If we made a y, we said that was 144. Terribly drawn to scale, but that's what it looks like. All right, thank you.